Hi, this is Sabir again. So, in this lecture, I'm going to discuss all about the symmetry of stress tensor. That means whether a stress tensor is symmetric or not. So, symmetry of stress tensor. Yep. So from the definition of symmetry of any tensor, so we know that any tensor, say T, can be decomposed to symmetric and both antisymmetric tensor. That means T is equal to tensor of Ts symmetric tensor plus T of antisymmetric tensor. What is Ts? So symmetric tensor is T plus transpose of tensor T divided by 2, and antisymmetric tensor is T minus, sorry, transpose of T divided by, so if we add this, then we will get T equal to T. That means any tensor can be divided and decomposed into its symmetric part and into asymmetric part. So whether a stress tensor is symmetric or asymmetric, so we'd like to know all about that. So from the stress we know, uh, the color, okay. Say any tensor, say any stress tensor T, right? Any stress tensor T here. So we know from the definition of T equal to F by A, right? So force per unit area, force per unit area. So in the stress tensor, so force is related to this. That means force equal to F equal to M A equal to V by T, right? So velocity is related to velocity or displacement is related to the stress tensor or something like that. So how we can do that? So from the static, so we know there is a definition, the static equilibrium or a static equilibrium of a body or something like that. So we'd like to let you know all about something here. Uh, what is that? I'm going to make you understand what is that. If we know all about that, then it'd be really helpful for us. A system of particles is in a static equilibrium when all the particles of the system are at rest. That means if there is applied force, then there will be no work of the force. Or if there is force, then equal force will be same, right? Yeah. The total force on each particle is permanently zero. So that means if we apply the three-dimensional case, right? So all the shear stresses would be the same, right? So if any stress sigma x y, and this must be sigma y x, otherwise so I'm going to make you understand all about that. So if anybody is in a static equilibrium, then the total force on each particle is should be permanently zero, right? Okay. So this is thick definition and often termed static equilibrium of a solid or any fluid, something like that, is used more relaxed manner, increasingly with the mechanical equilibrium. So this is also called the mechanical equilibrium also. Yeah, standard definition of mechanical equilibrium for a particle is the necessary and sufficient condition for a particle to be mechanical equilibrium is that the net force acting on a particle is zero. So for example, here we can consider a two-dimensional object here. Say it's a two-dimensional object. I'm going to. So if it is static equilibrium or in mechanical equilibrium, say it is x direction and this z direction. If it is mechanical equilibrium, then the rotation of the body, there will be no rotation of this body, right? And the body should be in rest. Body should be at rest, and it should be relaxed. And all the body forces should be zero. So how the body forces would be zero if the stress, if the if the difference between shear stresses are zero. So for example here, mm, this along this direction the shear stress is tau x z, and the opposite direction the shear stress tau x z, and that there will be no net rotation, something like that. Tau z x something tau zx. So these and this should be same or equal to 0. So say for example t zx should be t zx or t x z, right? So along this direction should be the same or something like that. So this should be the or this equal to the x z something. So if we write down t zx minus t xz equal to 0, so net force along this is 0. So for instance tensor something like that. So here we can write down, say for t equal to sigma xx tau xy tau xz tau yx tau yy, sorry, this should be sigma yy, and not all the normal components are denoted by the sigma, and here the sigma, sorry, tau yz, right? Yeah, so this is the tau zx tau zy tau zz. This is the stress tensor, for example, right? I'm going to change the color. It'll be so these are the normal components here, right? And these are the shear components. So these are normal components, right? These are normal components, and this normal components divides the stress tensor two segments. This three parts here, right? And again these three parts here, three components here. So these three components should be equal to this, and this tau yx should be tau xy, right? Because to make a body in at a static equilibrium, to tau xz should be tau zx. So what does tau xz means? Tau xz means is from the x plane and is directed towards z, and same way it's from the z plane it's directed to x. So the stress magnitude of this vector and this magnitude of the stress component should be same, because uh, this direction and this direction, if it's this direction, say for example it's x from x plane and x from z plane, and it's along the z direction, is along the x direction, right? So if the magnitude of these components and if the magnitude of these components is equal, right, then definitely then the difference between these two is 0. So the body would be the body should be at a static equilibrium, right? So there will be no net rotation of this body. So from the static equilibrium definition, it says that stress tensor is symmetric. So if this component is equal, and if this component is equal, and this component and this component is equal, then we can say this stress component or stress tensor is symmetric, and it must be symmetric, and it's real tensor, and it is symmetric something. Yes. So we can write down here. So from the similar definition, so we can here write down. So tau xy equal to tau yx. So this one. So tau xz equal to tau zx, right? And tau yz equal to tau zy. So these three shear components are same, but the magnitude of this shear components are same if it, then it's symmetric tensor. Yeah, it is symmetric tensor. So if its body should be a static, something like that. So stress tensor is symmetric tensor. Thank you, and I'm going to see you on the next lecture.